Okay, thank you. So this talk is going to focus on stream processing techniques, but more specifically, we're going to look at how we can use some open source tools to actually gain insight from real-time data. So in the first part of this talk, we're going to discuss what stream processing is. So if you're a beginner in this field, we're going to discuss a lot of basic examples to go over what we'll be talking about later in the demo. We're then going to look at some use cases of stream processing, as well as some of the challenges that are commonly interacted with when you're using real-time data feeds. We're going to look at some existing tools that exist in the Python ecosystem that you can use out of the box for using with streaming data. And we'll look a bit more detail into composable stream processing, or CSP, which is a newly open source library for this purpose. And lastly, we're going to have a demo where we actually take you through the steps of creating a streaming application using CSP, complete with backtesting on historical data, and then the transition to actually running that in real-time mode. So what we're going to be building by the end of this talk is going to be an interactive dashboard for different methods of transit. We're going to compute some metrics on real-time transit data and then display this in an interactive visual that you can actually move around and play with. So a bit about myself. I'm currently a quantitative developer at Point72, which is a hedge fund based in New York City. At Point72, I work on an algorithmic trading team where we regularly encounter live data in the form of market data. I've been a contributor to the CSP project since 2022 when I joined the firm. And we're really happy that we've finally been able to open source this project so that the entire PyData community can have access to this tool that we've been using internally. At their core, stream processors are just systems that react to events. And this is obviously a very general definition. So it's interesting to note that humans are naturally good stream processors, right? We constantly ingest audio data, visual data, or even sensory information as asynchronous streams of data. Our brain then uses that data and applies some transformations to that data, ultimately using it to update some internal state. And then you can use that data to produce some outputs, which would be decisions you make or maybe actions that you take within some environment. At a very abstract model, you can treat the stream processor as a black box. So it's taking in generally multiple asynchronous data sources. There's no guarantee of when you'll actually see events in this data. So for example, at time 1 in this diagram, the first stream has an event only. But at time 3, all streams have some event. And the stream processor needs to react to these and synchronize them in a relatively straightforward way so that it can actually transform the data, update state, and then produce some useful outputs, which generally are something predictive that you're running in real time or something which is monitoring a process, something like that. If we want to get really meta, we can actually look at yourself right now as a stream processor learning about stream processing. So what are the data sources here? Well, there's streaming data of me actually talking to you, which is actually asynchronous from the slides changing, which is the visual data you're encountering. And there's other streaming data that you just constantly ingest, like hand gestures, expressions of those around you. And all of this is actually used by the internal state in your brain to be updated, use your already learned Python knowledge, and then integrate that into some useful output. In the context of this talk, it could be an application for your own work, it could be questions you may have, or any insights that you have into the presentation. So stream processors at a basic level just do 3 things. What they do is they coordinate the input data that they receive, and this usually amounts to choosing how to order and synchronize events across different streams. There are 2 main approaches that libraries will take to this, and I'll discuss them in the next slide. After you've got the data into your engine, you then want to do transformations that are both effective and efficient. There are generally a couple of categories of transformations, which I'll go over as well. And once you have your internal representation, you then want to convert it to something useful, something that you can actually use outside of the process itself. And I'll discuss some of the commonly used data formats for streaming data. Something to note too is it's very important that your application works pretty similarly in both historical playback mode and real-time execution. Historical mode really refers to using simulated data, so you have a timestamp and some event, and then you play that back throughout your stream processor to see how it would have behaved. And this is useful for both research as well as testing. Real-time execution is using live data from a live feed. And I would say the biggest challenge in actually deploying a streaming application is the transition between the historical simulated mode and the real-time execution. So I'll discuss how you can deal with some of these challenges. The first step of the stream processor in any framework is actually coordinating the input data. And you have to choose how to order data and synchronize across different streams. So the 2 main approaches that different libraries will take is first using processing time. This refers to using the time stamp of when the event actually reaches your process. So the advantage of this approach is that it's quite simple. You see an event, you process an event. And it's also the most efficient way of handling events, right? There's no waiting for out of order or late data. You can process everything right when you see it. The other approach is generally more flexible, but it has those two downsides, which is processing by event time. This means that you're using some externally assigned timestamp on the event itself. So you can imagine having, say, two data sources, one that's on a slow network and one that's on a fast network. And you could have events that occur on the slow network, but actually reach you after the event on the fast network, just because of that delay between the event and your process. So a lot of frameworks will give flexibility in reordering events and waiting for out-of-order data. But this is quite complex for an introductory user, and it can also introduce latency into your pipeline by waiting for data. A couple of real-time sources that are often used in streaming applications, probably most common is Kafka. So Kafka is a messaging service with a nice pub/sub API where you can get real-time messages. You can also get data from WebSockets, from web endpoints, and any real-time source like that. Historically, when you're using simulated data, you generally have a timestamp column and some event data. So anything tabular works really well for this. My preference is to use Parquet, but there's also Polars or Pandas data frames, CSV, and anything that has really a tabular structure. So after you've got the data into your framework, you then have to actually do some transformations to the input. These generally fall into three categories. The first is what I would call control flow operations. So these are things that kind of change the structure of your stream, but they don't really do any computation. It could be something like a simple aggregation, filtering on some condition, sampling from the stream, merging or splitting streams. The second category is a bit more computational, and that would be a statistical calculation. So you often use a lot of moving averages on streaming data. This could be something like how many people have been on my website in the past 5 minutes, and what's the average time that they spent on the site. So you have a window which actively moves along a live stream of data to compute some metric. There are also expanding window calculations. It's like an exponential moving average. So you essentially use all data provided in the stream, but you give more weight to more recent observations. The last category is anything that isn't in the first two categories. So I would call that kind of more bespoke logic. This is just you have some Python code and you want to run it on real-time data. You could have, say, a pre-trained model to do live inference that you've trained in sklearn or Torch, and you then want to run that on live streaming data. So the frameworks kind of all offer some way to run your Python function on the data itself. However, some are easier than others. And lastly, after you've transformed your data, you then want to get it out of the process so that you can use it for whatever business logic you may have. The formats are pretty much the same as the input, Kafka for real-time, Parquet for historical. Something to note here is I mentioned that there's this discrepancy often between historical and real-time performance. So if you have an output which is predictive, sometimes you can notice very good performance when you're running that on historical playback data, and you can see the performance degrade in real time. And this is kind of puzzling. So what can happen is when you run a stream processing framework, historically, it doesn't account for the delay of your pipeline. So you have a simulated time, you have an event, and you get some output. What it doesn't account for is the actual time it took to get that output. So if you have very fast ticking data that changes rapidly, your output could be invalidated by the time it actually reaches the end of your process. And there's lots of ways that you have to kind of test for this when you deploy to real time. So in the next few slides, I'm going to discuss some of the existing solutions that, in Python. All of these are open source that you can use for stream processing. The first is Bytewax. So Bytewax is a nice framework with a nice Python API for stream processing, but a lot of their core logic is written in Rust, so you get that nice efficiency of the language. Bytewax has a very extensive library of pre-written transformations, so anything really in the first two categories of control flow and statistics, Bytewax already has for you. And they also have what I would consider very wide support for different data formats. So they have pre-written connectors, as they call them, for various database formats, various cloud storage formats. So if you're using these in your application, it can be quite a nice integration. Apache Flink is a very powerful but very complex stream processing framework, which is actually language agnostic. They have a PyFlink API for Python development. Flink is great for very large, complex pipelines, but it's not too good for an introductory user. They have a lot of complex but very flexible features. So I mentioned that some processors will use event time to reorder data and ensure consistency across multiple sources. Flink allows you to do this through a concept called watermarks, which is not unique to Flink anymore, but the concept is essentially you get events that are then queued up in a window, and you have to ingest another event into the stream that actually signals, hey, I can process the data that's waiting because I know from this point onwards, I'm not getting anything that's going to be late. As you can see, this is pretty complex logic. Like, how can I actually know when my data is coming in? Also, you have to wait to process the data. If you have a window, you don't have that window until you've actually seen the watermark. So this can introduce delay as well. But as I mentioned, it is very highly flexible. And if you need that sequential consistency across multiple sources, this is one of the ways to do it. Apache Beam is another open source framework which is interoperable with Flink. They're great for parallelization of highly parallel tasks. So if you imagine a process where you have lots of streams that are being run independently, the transformations on that data are not interlocked between the streams, then Beam can distribute that compute across different computers very well. And everyone has a multi-core machine these days, so it's something that you could do. Again, like Flink, the framework itself is not tied to a specific language. So they have multi-language support in Java and Go as well. So if you're not using Python, you can still use these in your application. A couple honorable mentions that I'll just put in. The first is Faust. So Faust is a pure Python stream processing framework, which unfortunately the company who made it discontinued maintenance for it, but it is still widely used. It's built on top of a framework called Kafka Streams, which is direct stream processing on Kafka messages. So if you have a pipeline that's essentially Kafka in, Kafka out, Kafka Streams can be a good choice for simplicity, since you don't have to go into one of these more complex frameworks. Or even if you have a framework where you're ingesting Kafka as well as other data formats, you can use Kafka Streams directly to do a pre-processing step and then give it to Flink Bytewax or something like that for a more complex operation. There's also Quix, which is built on top of Kafka Streams, and there's a couple other frameworks as well, which I didn't have time to go over, but I invite you to look at them as well. So in this kind of largish ecosystem, how does composable stream processing or CSP fit in? Well, in comparison to something like Flink or Beam, it's a lot easier to get started with. So if you have just kind of basic Python experience, you can create a day one example that you can actually run, which is quite nice. Like Bytewax, we have a lot of the common operations already written, and a lot of it's written in C++, so you get nice efficiency out of that. The API has no infrastructure constraints at all, so you can pull in data from any different data format that you want to, and you can actually write those adapters in either Python or C++ for performance. The historical to real-time transition is quite good because we keep our own engine time, and I'll talk a bit about that later. And like how Bytewax is written in Rust, CSP, all the core logic is written in C++, and it's actually extensible in C++ as well. So if you have a very critical bottleneck, you can write that function in C++ to get added efficiency. Some current limitations, in my opinion, since it is newly open sourced, is we don't support parallel execution. So if you have one of these highly parallelizable pipelines, like I was mentioning with independent streams, something like Beam or Flink is going to be probably more performant because it can distribute that compute. And also, we only have support for Python in the API right now. We do have a generic framework, but we've only written bindings towards Python. So before we go into the demo, I'm going to do a brief walkthrough of CSP, just so everybody knows kind of what the code is doing. I mentioned that stream processors really just do three things, and that's coordinate input data, transform that data, and then get it to some output. So in CSP, there's really just three concepts that you have to work with. There's input adapters, which take care of input data coordination. There's nodes, which are the fundamental transformation unit of the data. And lastly, there's output adapters, which much like input adapters, take your data from inside CSP into something else. You put input adapters, nodes, and output adapters together, and what you have is a CSP graph. And this is the actual application that you can run on your data. So a very basic hello world in CSP might look something like this. You have an input adapter, which is just the constant input adapter, so it's the most boring one you can think of. You apply this node, which is doing a very simple transformation. It's just putting that text into title case. And lastly, you have an output adapter, which, again, is just writing to standard out. Not too interesting. You can use the show graph utility from CSP to visualize this pipeline. And what you see is, again, the input adapter, a node, and an output adapter. So we can run this using the CSP run function. I set real-time equals true and the time to be now. And what we'll see is the message hello world printed at the current timestamp. The constant stream is just a stream that has one event, which happens at the beginning of the execution. So all we see is one message. We can also run this in the past. So CSP has a concept called engine time. What engine time is essentially self-awareness of whether the application is being run in real time or historical playback. So if your engine is being run in real time, the engine time is now. And if it's being run in playback, it's using the simulated time that it got from your data. So without actually changing the pipeline, we can run it on historical data. I'll give it some time in the past in 2022, and I'll set the real-time parameter to false. And what I get is the same message because I'm using the same data, but it's using a simulated timestamp of 2022. So you can imagine taking data, a year's worth of streaming data, and then running it back on your application. And something too is you can actually run a pipeline first on historical data to get to some state, and then continue running it without changing anything on real-time data as well. So CSP does provide built-in nodes for common operations like control flow and statistics, but oftentimes you have to do your own bespoke logic. And to do that, we provide the CSP node API. A CSP node is just a Python function which ingests one or more time series. The time series is the kind of fundamental data unit of flow in CSP, and all it is a stream of values. So whenever this text value gets updated, it's going to invoke this function, which does the following transformation. It just puts our string into Pig Latin. It's then going to return the Pig Latin string, and it's going to return it to another time series of strings. When it outputs that value, it'll automatically schedule any downstream consumers, so your whole pipeline gets executed in a nice fashion. We can put this together into a graph, which is our actual application. So we have two constants, hello and world. We apply the Pig Latin function to both of those constants, and we print the output. And what we have here is a slightly more complex, but still pretty simple pipeline with two inputs, one output, and a series of transformations. Nodes themselves are what I would call atomic units of computation. So that means that nodes pretty much do a singular function on the time series data. You can group nodes together, however, into graphs, and you can reuse those graphs to create even bigger graphs. So this is where the composability of CSP comes into play. Often in production on a real analytic pipeline, you'll have 10,000 nodes, 100,000 nodes, or even close to 1 million. So actually reasoning with this application and debugging it when inevitably something goes wrong can be quite complicated. It's much easier if you build up subcomponents, build those into larger applications, and then build from that. So in our demo, we'll see how you can actually take kind of smaller, more reasonable subgraphs and build them into something quite complex. Nodes themselves also have a couple other advanced features. So we're not actually going to use these in the demo. So if you're not following this entirely, that's fine. This is an example of how you can use per instance state as well as internal events to get some more advanced features out of a node. So this example is a Poisson counter, which is counting the number of events in a Poisson process. A Poisson process is just a random process where the delay is exponentially distributed. So what we do is we assign a state variable called the count, which is the total count of events. When the graph starts up, we then schedule an alarm with some random exponential delay. And whenever we have an event on that alarm, we can increment our count by 1, schedule a new delay, and then return the total count. So this is an example of some more advanced features that you can use to get better functionality within a node. So as I mentioned, there's really two execution modes for stream processing. There's the historical replay, which is often used for research and testing. Research side, you might want to see how your pipeline works with some predictive value and how it correlates with the target. And you want to then just deploy that pipeline to production without actually changing it. And testing-wise, you can test things in real time, but that's not very good for unit testing, right? Your network might be down. There might be other things that can create a lot of noise. So it's also useful for that purpose. The actual deployment you use, though, is going to use live data sources, which are streaming in actively. And a couple industries where this is often the case is, first off, financial markets. So you get lots of live price data from many different exchanges, and coordinating that data and transforming that data is pretty crucial. In transportation networks, you'll have multiple vehicles in a fleet, which you might be coordinating at some central processing source. Or you might have different modes of transportation, which is what we'll actually look at in the demo. On terms of climate analysis, we actually have an example on our GitHub where we look at different earthquake sensing stations around the world. And you can pull that data in to do some real-time inference on seismic events. And of course, there's many other industries and applications, which I just didn't mention here. But anything where you have asynchronous real-time data, and especially multiple sources, stream processing is the tool which is probably best suited for that purpose. So in the kind of more fun part of this talk, we're going to go through a demo of how you can actually create a stream processing application on real-time data. We're going to be using public APIs for transit data in New York City. So in New York City, the transit provider, which is the MTA, provides 30-second updates on all of their modes of transportation. So we can subscribe to APIs, which will give us subway train positions and delays, as well as the number of bus alerts and commuter rail alerts. We can then compute some metrics on this data and then display it. And also, every 60 seconds, the bike share provider provides updates on their stations. So we can see how many bikes are available across all of New York, as well as how many stations are full and how many stations are empty. Something to note is that these are all asynchronous real-time data sources, which is kind of that fundamental use case of where stream processing is most useful. So I'm going to go to my Jupyter notebook. I think I'll zoom in a bit so people can see that. So this notebook is pretty much going to create subgraphs to process every method of transportation independently, create some metrics that we can display, and then ultimately put those together in a final application which has our visualization dashboard. So the subway data, as I mentioned, updates every 30 seconds. The format of this data is this very kind of unique format called GTFS. It's General Transit Feed Specification. And it's kind of a wrapper on top of protobuf. So something to note is, as I mentioned, you can bring in any data to CSP and then do operations on that data. So we have written a GTFS adapter to actually bring that data in. The bus data is in JSON, which is much nicer to work with. And this is the same for the commuter rail data. And the bike share data is in this GBFS, General Bike Share Feed Specification format. But they actually just give it to you in JSON anyways. So it's quite nice to work with. The first step, as I mentioned, is just getting your data and coordinating. To do this, we use input adapters. So the two input adapters that we're going to be using is first off the GTFS adapter, and second off the JSON adapter. I didn't include the code directly just because of time constraints, but if you do want to take a look, these are provided in the GitHub that I have publicly available. So these are going to pull in data from our feeds in JSON as well as GTFS, and then pipe that information into the CSP graph. Our first subgraph is going to deal with the subway. So the metrics that we're going to compute for our dashboard is the average wait time for a subway train across all of New York City, as well as the 90th and 99th percentiles of that data, because you can always get unlucky and be stuck waiting for a train. So the first thing we'll look at is the static data provided to us, which is just the stop info. We can load this as a data frame. What we have is a list of stops, and we're going to do some filtering on this data. So we see that there's parent stations and there's also directional stations. When you're waiting for a train, you're going a certain direction. So we're going to filter out all of the parent stations. In addition, the New York City subway is actually so big that they expose 8 different API endpoints for the data. So we're going to use the main feed, which has 7 of the major transit lines. So we filter out all of the parent stops. We filter out all these lines that we're getting on the feed. And now we can actually get to the more fun part, which is doing our transformation to that data. We're going to compute, again, the average, the 90th and 99th percentile of this data. And we're going to store this all into a CSP struct. So a CSP struct is kind of analogous to a data class in Python, but it has this added benefit that each field of the data class can be accessed as an independent time series. So this is very useful if you want to access these as individual streams. In our wait time data struct here, we can look at the average, the 90th percentile, and the 99th percentile. To actually get this data, again, we're going to do a node, which is the transformation. So the node is going to ingest a time series of feed messages, which is coming from our adapter, as well as a list of stop IDs, which we're going to consider for our average. We're going to find when the next train is arriving at every single station. We're going to find how many of those stations were valid. And then we're going to compute the average, the 90th percentile, and the 99th percentile. We're also going to find how many stations are active or valid, meaning there's at least one train incoming, and how many are currently inactive. When we return this wait time data struct, it's going to return a time series, again, of wait time data objects. So it's going to schedule any downstream consumers that will then receive the data and process it sequentially. So we can run this again on historical or real-time data. Unfortunately, the MTA does not provide GTFS historical data, so I had to kind of hack this. I recorded the data to a Parquet file in bytes, and then we're going to load it back into CSP, convert those bytes to GTFS, and then do our transformations. Normally, you can actually just use the same adapter on historical and real time. In this case, we do have to kind of hack it a bit. But we can look at this hack and see we have a node that's transforming our bytes to messages. And then, after we have this, we can use the built-in Parquet reader in CSP to bring in that Parquet data. Finally, we can define our graph, the graph being the application. So if it's real time, we're going to use the GTFS adapter. Elsewise, we're going to load those Parquet files in, and then we're going to convert it to our format that we want, which is GTFS messages. And then finally, we're going to do the exact same pipeline of transformations on this data. So we call our wait time stats node, which is going to give us all of the stats we need. We can take a look at our graph by visualizing it, and we see that we have a parquet adapter as the input, we have a raw bytes transformation, and then a wait time stats transformation before we return from this graph. We can also just run this for 1 second in real time and see what we get. So the average right now in New York City is about 4.5 minutes for a train, but you could get very unlucky and have to wait 17 minutes. Again, we can run this on historical data as well. So the historical data set I recorded was about 18 hours worth of data. And if you run it all throughout an entire day in CSP, what you'll get is this. So this is the distribution of wait times on average across all of New York City. You see the average is very good. It's around 4 minutes consistently. The 90th percentile is only 6 or 7 minutes, so still quite good. But you could get very unlucky. You could have delays and wait up to 30 minutes for a subway train. The bus and commuter rail alert subgraphs are actually much simpler than the subway subgraph. All we're going to do is load JSON data into the CSP process and then do a couple of basic transformations. So the first is actually getting the type of alert that's being sent to us. Is this a delay? Is this a detour? What's going on here? We're going to put this together into a transit alert graph, which is going to ingest an endpoint and then give you a dictionary being the type of the alert to how many of those are currently active. So again, I can run this just for like 1 second in real time. And then I can plot the data using matplotlib. And we see right now the most common issue is just a boarding change. But there's also 35 planned detours and a mixed bag of other issues going on. We can also decompose these into either planned alerts or unplanned alerts to see if there's anything going on that's major in New York City. Again, we store these in a CSP struct with our total alerts, the number of planned and number of unplanned alerts. We do a count planned and unplanned function to get that data into a nice format, and we create an alert breakdown graph, being our application, which reuses the transit alert graph that we just ran, but just does this one extra transformation to the data. And we can run this again right now in real time, and we see that there is 41 planned alerts, and there's 95 unplanned alerts that are currently active. For the commuter rail data, it's actually the exact same. The data format's the same. Our transformations are the same. All we need to do is just give it a different endpoint to run on. So we're going to use data for the Long Island Railroad, which is the main commuter line in New York. And we can run this and see that there are a lot less delays and detours. And for the final subcomponent of our graph, we're going to use bike share availability, which I think is the most interesting feature. So City Bike exposes every 60 seconds the data in their station status. This means how many bikes are available and whether or not the station is active. So we can just do a quick request to see what this data looks like. You get a bunch of different fields. The most important one is the number of bikes available, but you also have the field whether the station is installed. We don't really care about stations that aren't installed. As well as, are they actually renting bikes from that station? Are there electric bikes available? And things like that. So it's a pretty comprehensive data set. The first thing we're going to do actually is take the JSON that we're getting and convert it to a pandas data frame. So the JSON format, isn't as good for tabular data as something like a pandas data frame. And what we're really doing here is tabular operations on columns. So we can do this first step of our data processing to actually convert it to pandas. And then we can do everything just using pandas like you're probably more used to. So the first step we're going to do is just a data cleaning step. We're going to remove any station which is inactive. Then we are going to just do some basic transformations like summating across a column. We'll use this to find how many bikes are available system-wide, as well as counting the number of stations where something is 0. This can give us how many stations are full, meaning that they have all the docks are full, and how many stations are empty, meaning that they have no bikes available. Again, we store this all into a struct, and we can define, finally, our availability graph. So we get our JSON data, we convert it to a data frame, we do data cleaning on that data, and we return all of the metrics that we've computed, which is the total number of bikes, total number of docks, as well as the station status. We can again run this very quickly in real time, and we see right now there's 2,200 active stations, 99 of which are empty, and 119 of which are full, and there's 29,000 bikes that you can take out. So we have these 4 kind of disjoint subgraphs, which don't really seem to correlate much with each other. What we can do is take them all together, put them into a large application, and then run that with visualization. So the final step is we're going to use a built-in integration between CSP and Perspective to visualize this data. Perspective is another open source library for data visualization in Python. So there's a built-in integration called the CSP Perspective table. Essentially, what you do is you can create your graphs, you can extract all your metrics and give them some nice name. Then you can load them into a pandas data frame with the name and the metric, and then you provide this to the perspective table, and it can do all these different types of visualizations for you. So we can take a look at the graph that we've created here using show graph. And as you see, it's a little more complex than you would have expected, right? You have all these different operations going on. You have 4 different data sources. But because it's quite composable, you can actually reason what's going on. This clearly is the subway data. These are the alerts. And this is clearly the bike data. So anything that is going wrong here, you can identify before you actually get to your final step, which would be what you're putting into production. And finally, for kind of the big reveal, I've been running this data for a couple hours so we can see some trends. So right now, we have the live data of the average wait time for the New York City subway. Consistently, it's around 4 minutes. We probably got some bad data here that ticked it up to 6. But we see these live updates coming in every 30 seconds on our streaming application. We can also use the interactive features to say how many bikes are available. It's going down because right now it's noon in New York. So as the morning kind of came into the afternoon, more people are taking out bikes and there's less available. We can see how many stations are full. So that's also going down a bit as people take out bikes. And you can look at all these metrics. You can use different visualizations as well. So we can do, say, a Y-line visualization. We can look at the average wait time. We can look at the 90th percentile wait time. I'm going to unselect that. And we can also look at, say, the 99th percentile wait time. And we get all of these visualizations actively in live updates. So what I want the takeaway of this talk to be is that stream processing is generally a powerful technique for dealing with live data. It can take care of all the coordination steps, and it can do all these transformations so that you really just have to worry about your own business logic. And composable stream processing in particular allows for this modular structure, which is much easier to reason with. So that concludes my talk, and I think we have a few minutes for questions.